Okay, we're now going to look at grammar in a bit more detail and what exactly we mean by grammar. What is a grammar? So things we're going to look at is it's an introduction to grammars. We are going to try and put it in the context of this thing called Chomsky's hierarchy, which is essentially talking about how powerful things are. So we'll do that after looking at what a grammar is and two very specific forms of grammars, which are regular expressions for doing regular languages and grammar notation in the form of BNF or eBNF. So a grammar is exactly what you think it is. A grammar is something that defines the structure of language. And ideally, grammar should be a precise definition of exactly what is a legal program, what is a valid sentence within this language. Grammars are linked to, but not enough to actually guarantee semantics. So a program can be grammatically correct, but it might be semantically incorrect. So there are lots of C programs, for example, or C++ in particular, where you can grammatically analyze it and determine exactly what everything is. But if you try and actually compile it, you find it doesn't actually have meaning. Grammars, as we see them, are used both by humans and machines. So for humans, they're often used in defining a language. That can be defining a software language or trying to capture an existing language. So trying to impose structure on things which don't currently have a well-defined structure. Grammars are also used a lot by machines, and one of the things we want to be able to do is communicate grammars between humans and machines. Essentially, you want to be able to write a grammar in a way that a machine can understand and do something useful with it. A particular thing you want a machine to be able to do is to automatically generate a parser for a grammar that you have defined. Once it's done that, once it's created a parser, the machine can then independently apply the parser to the input text without your involvement. So grammars are needed because languages tend to define unbounded or infinite size sets of valid strings. So in a grammar, I can usually use a finite number of rules, a countable small number of rules to define an infinite set. And you need to be aware that big does not mean infinite. So an example here used in class was if I look at the space of 1024 by 1024 by 8-bit grayscale bitmaps, I could have a surface representation in many ways. I could do it as a strings of zeros and ones. I could do it as strings of hex, but ultimately there would need to be some way of structuring that into 1024 lots of 8 bits, which means that the total number of bits in that is going to be 2 to the 23. That means that the total number of possible bitmaps that could exist is 2 to the 2 to the 23, which is massive. It's absolutely enormous, but it's finite. I could start generating every bitmap just by sort of going through every possibility, and sometime after the heat death of the universe it would actually finish, but it could finish. In comparison, if you consider C programs, because they're hierarchical and because you can nest things, you can always take a C program and from it make another C program. And within one C program there's usually at least one place, usually two places where you can add something, and typically there are n places, and every place where you could extend that program you would again find n or even n plus 1 places that you can now put things. So not only are there an infinite number of C programs, but as far as I know, due to diagonalization, there's actually an uncountable number of C programs. And in the context of what you've been doing, if you think of the input lines to your cache simulator, those lines themselves are actually bounded in a couple of ways. One of which is if you think of non-comment lines, then it's bounded by the address size, it's bounded by the data size. It's not that many characters. But even beyond that, I specified that input lines were no longer than something like 1020 characters. So again, you're looking at a possible input space of 2 to the 8,000-ish possible input lines, which is a lot but not infinite. In comparison, there are countably many well, an infinite number of input streams. It's countably infinite, but it is infinite. Okay, so looking for a semi-formal definition of grammar, we'll tighten this up a bit in a minute. The main things we have in the definition of a grammar is production rules, which are explaining how the left-hand side of a rule can be formed from the right-hand side. Within that, we use non-terminal symbols, which are sort of virtual things which don't appear in the actual text, and terminal symbols, which are the actual characters that we'll match against in the output. So here I can see all of the left-hand sides. So I'm defining an expression. I'm saying actually an expression can be this or an expression can be this. There are actually two ways of getting an expression. So on the left-hand side, I'm given the thing that's being defined. On the right-hand side, I'm saying this is a pattern that definition could have. So an expression could be bracket expression, operator expression, bracket, or an expression could be the literal x. Within those definitions, on both the left-hand side and the right-hand side, we can have non-terminal symbols. They're non-terminal because they have to be expanded again. So expression is a non-terminal because it's not a literal character that appears. I have to go over here in order to expand the expression, and eventually the expression will expand into something like x. The other thing I have is terminal symbols. So these are the things that will appear in the actual input text. These are the characters that I'm going to consume from the input stream as I work out what the program actually means. And once I've consumed all the characters, then I've parsed the entire thing. So one slightly confusing thing here is that sometimes we need to be talking about concrete specific grammars, and sometimes we need to be talking about abstract grammars or all grammars. So what I mean by this is if I were to talk about the grammar for C or the grammar for Java, that is a specific instance of a grammar. It has a specific set of rules. We also want to talk about grammars in the abstract. So this is talking about all possible grammars. So if you imagine the set of all possible grammars, a C grammar is a particular element from that set. But there's also this wider thing, which is the set of all possible grammars. And if I want to write algorithms that work with grammars, I want to think about all possible grammars rather than any one instance of a grammar. So in order to try and differentiate between these things, if we're talking about concrete grammars, so things like the C language grammar or a C language grammar, we'll see actual concrete literals appearing. So I know that plus, int and while are things that occur in C, and I would expect to see those things appear in my grammar at some point. In contrast, when we're talking about abstract grammars, we don't want to pin it down to any particular symbol, any particular terminal. So we're actually thinking about abstract placeholders like A, B, C, and these don't represent anything in particular except that they represent one single terminal symbol. So if these appear in abstract grammar, we are talking about something that in some given concrete grammar will turn into something like plus or int or while. Similarly, we need to think about non-terminals. So in a concrete grammar like for C or JavaScript, there will be a non-terminal called statement, probably, and another one called while loop. Well, they don't have to appear, but they probably will appear. And these represent sort of known fixed constructs because we're talking about C. If we're talking about abstract grammars, so all possible grammars, instead we talk about non-terminals as things like capital A, capital B, capital C. That's because we don't know what we're talking about in some sense. We only know the kind of thing we're talking about. And the kind of thing we're talking about, if we put a capital letter, is a non-terminal symbol, without knowing what that non-terminal symbol is. It's a placeholder for something real. Following that sort of theme, when we're talking about abstract grammars, one of the things we need to be able to deal with is sequences of symbols. So in the example we've been looking at, if we have expression followed by an operator followed by an expression, that's a sequence of non-terminals, and the order of those things is important. When we talk about abstract grammars, we have to have placeholders for these. So we'll use things like alpha and beta. So alpha and beta represent some sequence of symbols. A special sequence is epsilon, and this represents the empty sequence. So it's a non-terminal that has an empty definition. This is quite a troubling concept. We'll actually come back to this quite a few times, but just watch out for if you see a Greek letter and it's epsilon, you might want to think carefully about that, because it means that this thing can match even if no input is consumed. You can match this thing without reading anything. So one of the things we get with grammars is not only does it allow us to recognize things, it allows us to generate things. So here is our sort of basic grammar for expressions. What I could do with this is generate valid strings by randomly choosing one of the rules and expanding it. So if I toss a dice and I come up with this rule, the only way that I can expand this rule is with x, and so x is a valid sentence from this grammar. Here I've thrown the dice, and the first thing that's come up with is this production. That gives me this nesting thing, which gives me these two things. I then have to expand expression, operator, and expression. Again, I can throw the dice, I see, well, what kind of expression can I have? And this time I end up with this expression. So I can put an x down there. I throw a dice for operator and I end up with times. I throw a dice for expression and I end up with an x again. And I can produce different strings by, whenever I have some freedom, so this needs to be an expression, by randomly choosing one of the productions for expression. Something we won't cover too much, but it can be quite useful, is given a grammar, you can generate things which are almost valid strings. So I can choose to generate something that's completely invalid, and I can generate this in the full knowledge this will not match against this grammar, which is sometimes a very useful thing to do. I can also do things like generate things which almost match. So this doesn't match this thing, it doesn't match this, it doesn't match this. It looks like it might match to a human, but it's quite useful because it's wrong but in a non-obvious way. But we're not going to look too much at generating valid and invalid strings. We're mainly going to be looking at recognizing strings, so the opposite problem. So this whole thing of assigning bits of a string to things within the grammar is called the derivation of the string. So here's an example where we've got the same rules and now I've labelled them so we can talk about which rule it is. Here is our input that we actually want to parse, and our input consists of a sequence of symbols. And to start with, our sort of initial thing says we must match an expression. So if we look at this input and the possible productions for xbar, this cannot match x. It's wrong. Like, there is no x there, this whole thing is not x. So the only rule it can match is this thing here. So we apply that derivation, and that means we start to get some structure here. So this is this, which represents our first piece of structure. And as a consequence of consuming those literals, these two brackets here have disappeared. So we've actually matched those things in the original input, and we no longer have to try and classify what they are. Going on further, I've got an x here. If I look for what can match x, the only thing that can match that is this rule here. So this xbar and this x becomes this x replacing the xbar, and we've consumed the x over here. If we keep on going down, then now we've got a plus over here. The only thing that can match plus is this rule here. So that means that this plus has successfully replaced this thing here. And again, we're decomposing it further down. Now we're back in the same situation where we must match an expression here. And so this matches against this. And we can again strip off the brackets and we're left with the interior. And every time we go down, we're essentially moving things from here, as in characters of the input, and moving them over to here, which is terminals that appear within the structure. And we keep going down. Eventually we get to the point where there is nothing left. And happily, at exactly the point that we run out of inputs, we've also got rid of all of the non-terminals here. Everything has been replaced with a terminal, which means that there's nothing left to expand. So because this is a sort of well-formed grammar, these two things are guaranteed to happen at the same time. We finish the parse at the same time as the input is finished. Another way of looking at this is a sort of graphical decomposition, but it's the same process. So if we take all of our terminal symbols, some of these symbols we can immediately look at and say, well, multiplication, there is only one thing you can be. X, there is only one non-terminal you can be. So we could actually, in a bottom-up fashion, go through, and everything that we can assign, we could say, well, you must be an XPER, you must be an OPER. We can't do that with everything because we don't really know where a bracket should live, but all of these things we can immediately work out what they are. Once we know some of the non-terminals, we can actually put more structure on top. So here we have a situation where we have XPER, OPER, XPER. There's a bracket on the left, there's a bracket on the right. So that exactly matches the derivation, one of the derivations for an XPER. So we can build that structure up on top. And we've now taken 5 input terminal symbols and resolved them to a single non-terminal symbol. So if you look along the top, the total count of things that still have to be simplified is getting smaller. We can go one step further and we can match XPER, OPER, XPER, pair it up with these brackets, and now we've reduced all of these terminal symbols to a single non-terminal. And that means that for this input, the parse is complete because we've reduced all of the symbols to a single non-terminal. We could add things at the beginning and the end of this, so we could actually sort of prepend a bracket onto the front. We could put some extra symbols on the end, and in principle we could nest this thing in. So with all of these grammars, there's usually arbitrary amounts of nesting. But typically what we'll do is we will start from the beginning and go through to the ends. We won't do this kind of thing where we sort of tack things onto either side. Not all of the things in the terminals are actually useful. Once we built this parse tree, these brackets are no longer meaningful. I get all of the information associated with this tree just by looking at the things like what identifier is it, what operator is it. I don't need this structure anymore. It was just for the parsing thing. So some of the terminal symbols, which are often called punctuation, aren't meaningful beyond the point of parsing. And typically you wouldn't encode things like brackets in a data structure representing a parse tree because you just don't need them. They become meaningless after the parse. However, these things like x plus x are meaningful because we need to be able to distinguish between things like plus and times.